So 1-4 is about solving some equations. I want to give you a couple of tips before I show you an example. First of all, I want to remind you that that symbol, square root, always means the positive square root. Sure, 9 has 2 square roots, but the square root of 9, when I write the square root of 9, that means 3, not negative 3. The other thing is, if you square both sides of an equation, you have to check your solutions in the original equation. Let me show you by example what that means. Let's suppose I'm trying to solve this equation. The left side is the square root of 12 minus 2x, and the right side is x minus 2. I want to get the x out of that radical, and the only way I can think to do it is to square both sides. So I'll square both sides. On the left side, squaring the radical just gives me the 12 minus 2x that was inside there. On the right side, when I square that x minus 2, I get the first thing squared and the last thing squared and 2 times their product, so minus 4x. Now it's starting to look like a quadratic equation, except I got some x's here and here. Let's collect them all up to the left side. So I'll add 2x and subtract 12 from both sides. I add 2x, that gives me minus 2x here, minus 4x plus the 2 that I added. I'll subtract 12, so that's minus 8. Now there's a quadratic. I hope I can factor that because that's the easiest way to solve a quadratic. Let's try to factor it with backwards FOIL. Yes, I think if I use a 2 and a 4, then the last term will give me an 8. This will be a 2x and a 4x. I can manage to get negative 2x out of that. To get negative 8, one of these has to have a plus and the other has to have a minus. To make that negative 2x, I think I want minus 4x plus 2x. Make that a minus and this a plus. So the only two solutions of this, look, here's a pair of numbers that equal 0. So 0 is very special among the real numbers. If the product of two numbers is 0, one or the other had to be 0. X minus 4 has to be 0, or x plus 2 has to be 0. But that means x is 4, or x is negative 2. But at this step, I squared both sides. I have to check these back in the original equation to see if they're right. Let's see. When I check x equals 4, I get the square root of 12 minus 2 times 4 equals 4 minus 2. Does it? Let's see. That's the square root of 12 minus 8 is the square root of 4 is 2. Yep, the square root of 4 is 2. But if I check negative 2, I'll get the square root of 12 plus 4 is negative 2 minus 2. That's the square root of 16 is negative 4. Well, 16 has 2 square roots, but that symbol means the positive square root of 16. So this is false. The square root of 16 isn't negative 4. The only solution is x equals 4. Here's another. If I square both sides now, I'll get the first thing squared, that'll make that radical go away, and the last thing squared. But then I'll have 2 times their product, and I'll have the square root of 3x minus 5 times the square root of x plus 7 again. The radicals won't have gone away. So here's the trick. I'm going to get one of the radicals to the other side. I'm going to add the square root of x plus 7 to both sides. I could also have subtracted the square root of 3x minus 5, but I'll just choose to add the square root of x plus 7. Well, I worked out this bit and I want to show you how it turns out from here. So I want to get rid of the radicals by squaring both sides. Now when I square the left side, it's easy. I just get 3x minus 5. But when I square the right side, there's a sum there, so I have to FOIL it out. Or just remember how the square formula goes. I get the first thing squared and the last thing squared and 2 times their product. So you see, when I squared just the radical goes away. But when I've got something plus a radical, squaring it doesn't make the radical go away. So can you see how I'm going to get rid of this one? I have to get this other stuff, the 4 and the x and the 7, to this other side by subtracting. I'll get this radical here by itself so that nothing's being added to it, and then I'll square both sides again. So I subtracted the 4 and the x and the 7 from both sides. So I'm just left with 2 times 2 times radical x plus 7 on that side. And this was 2x minus 16. And then you might notice that both sides are multiples of 2. You could make life a little easier if you divided both sides by 2. So I factored a 2 out of the left side. It's 2 times x minus 8. And now divide both sides by 2. So I've just got x minus 8 on this side. And instead of 4, I have 2 radical x plus 7. I don't need to get rid of that 2. When I square both sides, the square of a product is the product of their squares. Right? Good old laws of exponents again, that says, a times b to the n is a to the n, b to the n. It's a plus b to the n. That's much more complicated. So I square both sides. So I square the 2, I square the radical. I use the formula for a square. It's the first thing squared, last thing squared, and 2 times their product. So that's 4 times x plus 7, or 4x plus 28. Now it's a quadratic equation in the sense that the only thing that happens to x is x is being raised to the second power and to the first power, and some numbers being multiplied by those things. Let's just collect up terms, get a 0 on one side, and we'll try to factor the other. I subtracted the 4x and the 28 and got here. I was able to factor that. I got x equals 2 and x equals 18. But because I squared equations, these could be solutions to other equations. I've got to check that x plus 2 actually works in the original equation and that x plus 18 works. So let's see. I plugged in x equals 2 and I got at x equals 2, this is the square root of 1 minus the square root of 9 equals 2, and that's false. That's 1 minus positive 3. That doesn't equal positive 2. So I ruled out x equals 2. At x equals 18, this was the square root of 49 minus the square root of 25. That's 7 minus 5, that is 2. So x equals 18 was our only solution. So I just want to show you something. The author calls these homework problems equations that are quadratic in form or something like that, but they all illustrate a general trick for solving equations. If you don't, some equations are so simple that you can solve them right away, but if you can't, then there is this general trick that we use to solve equations. You get a 0 on one side, you factor the other, and then you set each factor equal to 0. And I want to show you just an example of that we did with quadratics. Let's suppose I was trying to solve that equation, x squared minus 7x minus 8 equals 0. So I managed to factor the left side, and now I use the fact that if the product of two numbers is 0, one or the other had to be 0. So when I set each factor equal to 0, I get two simpler equations to solve. They're so simple, in fact, that I can just solve them. X has to be 8 and x has to be -1. So that's what this trick does, is it replaces one equation with two or more simpler equations. As many equations as you have factors when you're factoring that guy. So let me try another example. Let's try, say, this one. X to the 6 minus 7x cubed minus 8 equals 0. Well, that has three terms, and the trick that allows me to factor it is to recognize that that's like a quadratic equation. It's just like the previous equation, because x to the 6th is x cubed squared, right? The laws of exponents say that when you raise a power to another power, the exponents multiply. So that is the square of the x cubed that I see there. This is just like the previous problem, except that the x's in number 1 have been replaced by x cubed down here. So it must factor the same way. So when I set each factor to 0, I still get simpler equations than before. Are they so simple that I can solve them? Well, I think I can, because now all that's happening, a real clue that you can solve an equation, is when x only appears one time. And some stuff is happening to it, but you can solve for x by undoing the things that happen to x. Like, here the x is being cubed and 8 is being subtracted from the result. So the first step I do is to undo the last operation performed here. That's that subtraction of 8. I'm going to add 8 to both sides. Now the next thing I want to do to both sides to undo the stuff happening to x is something that would undo the cubing. Well, that's cube root. What's the cube root of 8? It's the number whose cube is 8, that's 2. And over here I can do the same thing. X cubed has to be -1. X must be the cube root of -1. That's -1 because, -1 is the number, so that when you cube it, you get -1. So -1 is its own cube root. Let's say x minus 7 root x minus 8 equals 0. That's starting to look familiar. Look, I've got the same -8, -7 in all these examples to make the examples easier to follow, I guess. But look, the thing that allows me to solve this one like I did the earlier ones is that that thing, x, is the square of that. So this is like a quadratic equation. It's like example 1, except that the x has been replaced by radical x. So I think I can factor it like this, with radical x's here and here, instead of x's. But it's still -8 plus 1. So here I've got the product of these two numbers. And you can FOIL this out and double check. This does equal that, but it does because it's exactly like example 1 again. Now I've got this product of two numbers equals 0. The only way that can happen is if one or the other equals 0. So I'll set this equal to 0 and solve. I'll set this equal to 0 and solve. So that's square root of x equals 8. Square both sides, that's x equals 64. This says square root of x is -1. Now wait a minute, I could square both sides and get that x equals -1 squared, but that's a problem. I'm supposed to notice right here that that's impossible. It's because whenever anybody writes the square root of x, they mean x has to be positive, but that this radical is also positive. That square root refers to the positive square root of x. It's impossible for anybody's square root to equal -1. Sure, there are numbers, -1 is a square root, it's a square root of 1. But that symbol always means the positive root, so that has no solutions. The only solution to this problem is x equals 64. If you squared this thing and said, what if I didn't notice this and I squared both sides? Well, the square root of x is squared and the -1 gets squared, and that would become x equals 1. Okay, if you had squared both sides to learn that, you could still have it. There's still a chance that you would catch your mistake and realize that 1 isn't a solution, because remember, if you square both sides of an equation, you have to check your answer back in the non-squared version. So before squaring, we had that equation. And if you plug it in, the square root of 1 doesn't equal -1. Again, this symbol means the positive square root. So after squaring both sides, if you check here, you'd have to rule out x equals -1. And x equals 64 is the only solution. I guess I squared both sides to go from here to here, but the square root of 64 is equal to positive x. So I can see that one works. Let's see how much mileage I can get out of this one example. Maybe I won't have to do any other quadratics than this one today. How about this one? I guess there's two ways to do this problem. You could multiply all this out and distribute the 7 through there and collect up terms. This must be some quadratic that we can factor. But in fact, because this term is the square of that one, this must be just like the previous problem. This is like number 1 again, with the x replaced with x plus 3. So I already know how to factor this. It must be x plus 3 minus 8 and x plus 3 plus 1. So I'll set each factor equal to 0. And in this, I guess, this is x minus 5 equals 0. X equals 5 is a solution. This is x plus 4 equals 0, so x equals negative 4 is the solution to that. So it's a solution of that quadratic as well. One more trick I can show you, and I'll use the same numbers to save time. Let's try this equation. So 1 minus 7 over x plus 1 minus 8 over the square of x plus 1 equals 0. Do you remember this trick earlier? If you want to get little fractions out of the equation, and if you want to get fractions out of the equation, multiply both sides by the denominator. So if I multiply both sides of this by, both sides of the equation by x plus 1, that would cancel that one, and there wouldn't be a fraction here. If I multiply this by x plus 1, some stuff would cancel, but I'd still have an extra x plus 1 in the denominator. So the thing I want to multiply both sides by is x plus 1 squared. So multiply both sides by x plus 1 squared like that. So 0 times x plus 1 squared is still 0, but when this guy hits that, I get x plus 1 squared. When this hits that, there's 2 x plus 1's in the numerator and 1 in the denominator. So after canceling, there's 1 x plus 1 left in the numerator, like that. And when this hits the last fraction, the denominator cancels completely. I'm left with minus 8. And 0 times this is 0. And now it's a lot like the previous problem. I could either multiply this out. If I don't recognize how to factor it, I could multiply all that out. But if I'm clever enough, I'll recognize that that's the square of this. So this is just like a quadratic where the x has been replaced by x plus 1. So that's minus 8 plus 1. And I can set each of those equal to 0 and solve as before.